Hi, I'm Marie Coolsaet, a data science specialist at Snowflake. I'm going to help you understand how model training and deployment happens in Snowflake using Snowpark for Python. This is super valuable for data scientists because you're training and scoring models right where the data is. And if you're interested in data science, you should also learn about Streamlit and the Snowflake Data Marketplace. So we'll cover those too. To learn about all of this, we're going to help food trucks from the fake company Bytes find a place to park. We'll build a model that predicts the shift sales at each location. At the end of this, we'll have this cool Streamlit app that uses the model deployed in Snowflake to show shift sales predictions by location. Before that, we'll go through this notebook to show building and deploying the model. However, our first step is to get our third-party data from the Snowflake Data Marketplace. So this is a really awesome place to find data, to enrich your analysis, to feed to your models. Basically here, you share data and it's just a permission change. So no copies of the data are being made. There's no movement of the data. You simply get access to it and you can query it for your own purposes. We are going to use it to enhance our location data. Bytes operates food trucks in cities across the globe, with each truck having the ability to choose 2 different selling locations per day. The locations are mapped to SafeGraph points of interest. So we want to join latitude and longitude from the SafeGraph marketplace data to our shift sales data to use as features in model training. So first step, let's find that SafeGraph dataset. And luckily, they've published a dataset just for Bytes. So we select this SafeGraph Frostbite data. You can see it's free and available to query. We click Get. And then from here, we're going to rename the database to Frostbite SafeGraph. And then we're going to grant this role to public so that we won't hit any permission errors. And then Get. And now we have access to that third-party data. It's not being copied over. We're not paying for storing it. And we can query that data. We're going to query it in our setup script. So let's move to our setup script. And I know setup is often quite boring, but this one is pretty simple. And there are some neat things that can be learned here. So in the setup, first we're setting our role. We're doing this as account admin. Typically, you would not be working as account admin. You would be working as, say, a data scientist role. And with that, you would need to have each object granted to you for you to be able to use it. We're using account admin just to simplify the process so we have access to everything. And then we need to create our database. We're going to be using this for data science. So it'll be a dev database. Typically, as we're developing, we don't want to be touching the production data. One thing that's really cool about Snowflake is that you can make a 0-copy clone of that production data, so the data the data scientists are working on looks exactly like it. And then we're going to follow some data engineering best practice here and set up 3 zones: our raw zone, which is where we'll ingest our data into, our harmonized zone, where we're going to transform data, and then finally our analytics zone, which is where our data scientists or our analysts can access the data. And these are schemas within our database. So easy to define and set that up here. And then we're also going to create a file format. This will allow us to ingest the CSV data files into Snowflake. We'll define an external stage pointing to our S3 bucket. Currently, our data is in CSVs in an S3 bucket. We're going to define our table that is going to be brought in from CSVs. This is the first point. We're going to use a compute warehouse. So we're going to create a new warehouse that auto-suspends after 60 seconds. And then we're going to use that warehouse. And now we're going to copy in the data from S3 into the table we created and defined. So this was in our raw schema. Now we're going to combine our SafeGraph data with that shift sales data in our harmonized zone. So here we're joining in that safe graph data that we brought in from the marketplace. And finally, we're going to promote our harmonized table as a view to the analytics zone for our data scientists to use. This is what we'll be using for the rest of this project. And we can view that data right here. So what we can see, we have our location ID, the city it's from, date, the shift sales, if the shift was in the morning or the evening, what month it was, day of week, city population, and we have that latitude and longitude from shift sales. So this is a combination of the data we brought in from S3 along with our third-party data from SafeGraph. Next, let's move to the notebook. The main purpose of this notebook is to build a data science model. So I'm using Jupyter notebooks in a local Python environment, and our mission is to help Tasty Bytes to achieve their goals, which is they're aiming to achieve 25% year-over-year sales growth over 5 years. So as a Tasty Byte data scientist, I've been asked to support this goal by helping our food truck drivers more intelligently pick where to park for shifts. We want to direct our trucks to locations that are expected to have the highest sales on a given shift. This will maximize our daily revenue across our fleet of trucks. So our model is going to provide the predicted sales at each location for the upcoming shift, kind of like in this diagram here. And this is going to be an introduction to Snowpark for Snowflake. We're going to use Snowpark to explore the data, perform feature engineering, train a model, and deploy that model in Snowflake. Why Snowpark? A huge reason is that there's no copies or movement of data. You can maintain the same governance that you have in the Snowflake platform, and you can leverage that Snowflake scalable compute. That comes in very handy. Let's start by getting to know Snowpark with just the basics like connecting and how to work with data frames. So with Snowpark, we import packages just as you would import any other Python package. You can see here we're not only importing our main tool, which is the session that helps us to communicate with Snowflake, but also functions that make it easy to perform different operations and use different tools included with Snowpark. And then also here we're importing the window function, which will allow us to create some rolling features that are very nice, especially when you're forecasting into the future. And then we're going to connect to Snowflake. So here we're using our Snowflake credentials, our account, our user, password, the role we're using. So we're using that account admin, our warehouse, the Tasty Data Science warehouse that we created. This warehouse could be completely dedicated to data scientists so you can track their activity and usage of the platform. Our database, which we just created and set up, and then also the analytics schema. And then we use that session object to connect to Snowflake. Next, let's start exploring Snowpark data frames. So we're going to create a Snowpark data frame containing our shift sales data from the shift sales view in our Snowflake account using the Snowpark session.table function. A data frame is a data structure that contains rows and columns similar to a SQL table. So this is a very familiar representation of data for a Python user. And next, we're going to take a look at that data. So we're going to use the show function here, and then we'll be able to see our data. One thing we're going to notice is that there's a lot of null values in shift sales. So let's investigate that a little bit to figure out what's going on there. So now we're going to use some of those data frame functions to manipulate our data. We're going to select the data we want. We're going to select date, shift, shift sales, location ID, and city. We're going to filter to a single location ID and then sort that data by shift. So again, this chained syntax here is very familiar to Python users, and it's really handy and efficient if you have a lot of complex transforms, which sometimes isn't the case if you're just using SQL. So now we can see that the null values represent future dates where we don't have the shift sales for it yet. So speaking of SQL versus Python, Snowpark works in two main ways. The first is the data frame API query, which we were just working with. With this, everything is translated into SQL before it is executed in Snowflake. As we saw, those transforms, so selecting, filtering, sorting, are all simple SQL statements. So those would be transformed into SQL before executing in Snowflake. The other one, which gives us data scientists a lot of power, are the Python functions. So this is being able to bundle up Python code and deploy it in Snowflake. It then executes in a secure sandbox within Snowflake, and you can take advantage of all of our favorite packages, scikit-learn, Keras, NumPy, Pandas, and use those within that function within Snowflake. So let's look at above when we were using that location DF data frame that had been selected, filtered, and sorted, and see how that executed in Snowflake. So the translated SQL query can be seen in the Snowsite interface. Let's actually go take a look at it here. So if we go back to our interface and we go under activity and query history, we can actually see the query here and the underlying SQL that executed when we did that select, filter, and then sort. But if you don't want to be flipping between the interface, you can also use the explain function, which will tell you the underlying SQL and also how it's being executed. And one last interesting point is if we compare the size of a Snowpark data frame to a sample Pandas data frame. So here we're bringing 10,000 rows of our Snowpark data frame to Pandas. So we've brought this local, it is now existing on my computer, and we get the size of that Pandas data frame versus the Snowpark data frame. We can see the Pandas data frame is using memory, but the Snowpark data frame is not. So the Snowpark data frame, no data is being brought over locally. It's staying in Snowflake. The Pandas data frame is running and existing locally. We really just want to emphasize when you're using Snowpark and the data frame API, no copies or movement of data are made. Next, let's get into data exploration. We're going to use Snowpark to explore our data. A common pattern for exploration is to use Snowpark to manipulate our data and then bring an aggregate table to our Python environment for visualization. So the value here is that you get to use native Snowflake performance and scale for aggregating large data sets, and then easily transfer that aggregate data to the client-side environment for visualization. So as we explore our data, I'll highlight what is being done in Snowflake and what we are transferring to our client-side environment. In this case, the Python notebook environment for visualization, because I want that to be really clear. So first, we're just going to count how many rows are in our data. And we can see it's almost 2 million rows. So this is good to do anyways. It will give us a sense of how we need to handle this data, if we can even work with it locally. But what's happening where? So our rows are counted in Snowflake and no data is transferred over. We're using one of the Snowpark functions here. Next, let's calculate some descriptive statistics. Here we're using the Snowpark describe function, which automatically gets the min, max, standard deviation, mean, and count of all of the features within our table. And then we are transferring just this table that you see here over to our client-side environment by using two pandas. So next we want to know what our different column types are. So what are our numeric columns? And for this, we're actually just using the Snowflake table schema to get the metadata information about the data. So no data is transferred, and we're not using any compute in Snowflake either. And same for the categorical columns. So the model we're using today can't handle categorical columns, so we need to pay attention here. Shift is one that we're going to have to modify to make that numeric. And now let's begin to understand what's normal in our data, what a normal shift looks like. So we're going to create an analysis data frame by grouping our data by city and aggregating by the mean shift sales. We're going to sort that and then bring it to Pandas to plot the shift sales by city. So we're doing the grouping and averaging of sales in Snowflake and just transferring that aggregate table to our client side so that we can do this nice plot. And we can see if we look Sao Paulo at the top, San Mateo at the bottom, it looks like it is roughly corresponding with population, perhaps. And now let's look at a single city. This model will be used by a truck driver who only picks locations within a single city. So what does this look like within one city? So again, we are going to filter to just that one city, and we're going to group by location ID and get the average shift sales for each location ID. So the first question is how many locations are in the city we're looking at, which is Vancouver, Canada. And we can see there's 435 locations. Again, this was all done in Snowflake. No data was transferred. And then if we want to plot the distribution of our shift sales, so we can see here where the highest bars are, this is the most common shift sales amount. So most common is around $200 per shift, with the low end being around $160 and the high end being around $260 per shift. Now that we've explored our data, let's move on to preparing it for modeling with feature engineering. We will create a feature engineering pipeline by chaining transformations to prepare our data for model training. So the Snowpark syntax makes pipelines easy to implement and understand. All transformations for feature engineering in this notebook will be executed on Snowflake Compute. So the first feature we're going to do is create a rolling average feature using that Snowpark window functionality. This will allow every row in our data to get the average up to that point. This is very useful when working with a forecasting problem. Next, we're going to impute missing values. So the rolling average feature I just created is missing if there are no prior shift sales at that location. I want to replace those missing values with 0. I'm going to encode the categorical columns. So our shift feature, which has AM and PM, we now need that to be represented as 1 and 0 so the model can take that value into consideration. And next, we're going to filter to historical data. As we saw, there are some null values representing future dates in our data, so we want to remove those from our data. And then we'll drop the columns that we won't need in training, like location ID, city, or date. And then we're going to split our data into training and testing using the random split function within Snowpark. So it's going to split it into 80% for training and 20% for testing. And then we'll save these tables in Snowflake and then move to model training. We are going to train a linear regression model on Snowflake. Up to this point, we've been using the data frame API with Snowpark. Now we're going to get to use the Python functions deployed in a secure sandbox in Snowflake. So we'll be leveraging the deployment of Python functions into Snowflake for training and model deployment. So here we see a typical data science workflow. We are finished preparing our data, and now we move on to training in a Python stored procedure on Snowflake. The model created from the stored procedure will be our tool for automating decisions around truck locations to maximize our revenue. We'll surface the predicted sales model inference on future data using a Python user-defined function to drive decisions. Snowflake stored procedures work well for training because they can read data, hold an entire table in memory to find patterns, and write files, like model files, back to the Snowflake database. Snowflake user-defined functions work well for inference because they return a single value for each row passed to the user-defined function. Because of this, they can easily be distributed to provide fast results. And what we see here with this process, effortless, scalable, and secure processing without data movement across compute environments. So we won't be pulling anything locally for this training and deployment process. The first step we need to do is create a stage. This is going to hold our user-defined function, stored procedure, and model file. Then we're going to create our stored procedure for model training. The first step is to create a function for training a model. This function is a scikit-learn linear regression model and saves the model to a stage. Linear regression finds a line that best fits the data points used in training. We then use that line as an estimation of where output values will be for future scenarios. So here, training will use historical shift sales and features in our data to predict future shift sales of locations where our food trucks can park. The inputs here is our training table name on Snowflake, the feature column names, target column names, and file name for the saved model. The cool thing about setting this function up like this is that it can be reused for other problems outside of shift sales if you can define the target and the columns and provide the data table. The output here will be the feature weights of the trained model or feature contributions to the predicted value. So we define that function. Currently, this would work locally, but we're going to register it on Snowflake. So to make this happen in Snowflake, we need to deploy it in Snowflake, and we do that by registering the stored procedure here. An important part of this registration is that we say what Python packages are required for this function to work. So that's going to be Snowpark, scikit-learn, and then also joblib, which we use to package up the model. So we are taking advantage of the hundreds of Anaconda managed packages which are deployed in Snowflake that our functions can access. Okay, now we're actually going to train our model. And we do that simply by calling our stored procedure. So here we're defining our training table. We're saying the model name of what it needs to use, and then also the feature columns that are going to be used for training in our target column. And we call that model, and it will train here. So we are just using a standard compute warehouse for training, but often if a data science or a modeling problem requires more memory, we also have Snowpark optimized warehouses that can provide much more memory for training purposes or other data science purposes as well. Now that this has run, we'll examine the feature contributions. So this is what we set our stored procedure up to return, which is really nice because it doesn't mean it's a black box process. We're throwing this function off into Snowflake and we never know exactly what happens. We can return the insight we need if we want. And what we can see here, we can see the weights of the different features. So this one shows when the shift value is 0, it would bring the contribution to 0. But when it is 1, so in the morning, it brings down the expected shift sales by 12. So we can see that potentially people are hungrier in the evening shift. And then we can see the saved model on the stage. So it's successfully saved to the stage. The next step is to deploy that model. We want to make our model available in a central location where it can be used by other users and teams. At Tasty Bytes, how this model could be used is the application development team might want to integrate it into the truck driver app. The analyst team might want to benchmark and measure the impact on sales. As data scientists, we will want to monitor the performance and work to improve the model. But what we actually want to do as soon as we deploy this model is create a Streamlit application to prototype how this model could be leveraged in an app or by users. So that will be our main motivation in the short term. So if we're going to be using this model by many different teams, what better location to deploy the model than where the data is being used by these teams? So we need to create a user-defined function for model inference. This is a very similar process to above, that you start by creating a function that does the model inference and then registering that function onto Snowflake and specifying the packages required for it. So in this function, our inputs are going to be the model features and our output is going to be the predicted shift sales. Because we specified the input as a pandas data frame and output as a pandas series, so here you can see the input as a pandas data frame, output pandas series. The user-defined function will execute in batches instead of one row at a time. So in many cases, this reduces the overall execution time for the query calling the user-defined function, especially if the main functionality you're using here, so model.predict, is set up to handle vectors or arrays of data, which in scikit-learn it is. We also get another efficiency boost here by using a Python library called cache tools, which caches the model that is returned from the load model function. If we didn't do this, say this wasn't set up in batch and the UDF was called for every single row, it would reload the model. By caching it, then it only does it once for the call. So both of these help the inference to be fast and efficient at providing predictions. So as before, we've defined our function here. This is the function that's going to predict sales. First thing it does is loads the model by calling this function here that is cached, and then it gets the predictions and returns the predictions. So next we register it on Snowflake. We specify needing scikit-learn, joblib, and cache tools, and we say the import. We specify that we want it to include the import of the model file so that it's able to load that. And now what's left is to predict. So the first thing we're going to hear is we're going to take advantage of Snowflake's scalable compute. With our user-defined function, it can be distributed and run in parallel, but if we have a single-threaded or single-node warehouse, it won't. So we're going to scale up to a medium warehouse to speed up our prediction. And we'll test this out by calling our user-defined function within Snowflake. So we are using the data frame API here to select our shift sales and then call the user-defined function that we've created and call that column prediction. So then we can see the shift sales versus the prediction coming from the model. We can evaluate our model again by using a combination of the data frame API and calling that user-defined function. So we're going to calculate the root mean squared error here for both training and testing. And now let's show how we can use the model. So this is going to be the core idea of our Streamlit application, except the Streamlit application will be more dynamic. So we're going to look at how the model could be used for a single city if a truck driver was trying to find where to park. So we're going to filter to the first future date in our data and Vancouver locations again. We'll then call our inference user-defined function to get predicted shift sales at each location. And then once we do that, we're going to bring our predictions locally to pandas. And again, that's just the aggregate. So for each location, we have the prediction, and then we're going to plot it on a map. And we can see the yellow here is what we want to find. Those have the higher predicted shift sales. And we can see there's a good spot with predicted shift sales of $2.99. There's another one. So the truck drivers can use this to figure out their day and pick which locations they're going to pick. But one thing here is this is not very accessible to other users to understand how to interact with the model, to try it out, see if it's something that would be worthwhile to them. It's also not very dynamic. Say we want to change it to the PM shift and see the output, or say we want to switch to a different city and see the predictions. That would all have to be coded in here, which is why we're going to use the Streamlit app to allow users to interact with the model to really see if it's something that would bring them value. Here we are again in our Streamlit app. As you can see, it's very similar to what we saw at the end of the notebook, where we have this map with each dot representing a location. The darker the dot, the higher the predicted shift sales. Those darker dots are the ones we would want to direct our food trucks to. The main difference here is we can now interact with this directly. This could show the updated shift sales. Say I log in tomorrow and I want to see the next predicted shift sales. I can get those. You can also navigate to the city that you care about. So say you want to go to Vancouver, like in the notebook. We select that, and instead of AM shift, we want to look at PM shift, and then we can update it. So this allows a user to interact directly with the model. You can see we're getting the predictions now. And what's happening here is we're using that user-defined function that we deployed our model into to get the predictions for this specific city and for the PM shift here. And then we can zoom in and see these locations. So this makes it very accessible for other users, and it's very easy to build this app interface. So I'm going to show some of the code behind this to highlight the ease of use and development here. So this is a Python script. This app is fully developed in Python. Streamlit was recently acquired by Snowflake, and it's being more and more integrated into the foundational platform of Snowflake. However, at its core, it was an open source package, and its main mission was to make easy app development all in Python. So it has many objects like Streamlit header to define our title, Streamlit subheader to define the subheader in a slightly smaller font. So you don't need to code any of these objects manually. And if I point out some key aspects here we are connecting to Snowflake the same way that was done in the notebook. And we're caching this so we're not continuously connecting to Snowflake. It will only do this every hour. And then here's where I define those filter dropdowns. So I use a select box object for city, and then I use the selection radio object to define shift AM or PM. Whatever's selected there is going to be saved by that variable, so I can use it to filter the predictions. So next, I have this predictions function that takes in that city and shift, and this walks through the different feature engineering steps we did in the notebook. So that includes calculating the rolling average using the window function and imputing the data, the zero values, encoding our shift sale from AM and PM to 1 or 0, and then calling our user-defined function. So we're using that data frame API, we're using that function deployed in Snowflake to get our predictions for the upcoming shift sales. And we add a Streamlit button here. And then if it's selected, so if you click update, then we're going to call those predictions and get those predictions. So when we click update, we're running through the feature engineering pipeline and calling the user-defined function. And then finally, we display it in the map. And that is everything that's behind our Streamlit interface here. And it's totally powered by Snowflake. All right, let's recap what we learned here. We accessed location data from the Snowflake Data Marketplace and used it as a feature in our model. We used Snowpark data frame operations to explore and prepare our data. We trained the model in a stored procedure and deployed it for scoring in a user-defined function, all within Snowflake. We built a Streamlit app to leverage model predictions and identified the best locations to park. All of this was done without copies or movement of data. Pretty cool. If you want to try it on your own, check out the Quickstart linked here. Happy building!